going to talk about relations and functions. And functions turn out to be quite an important thing in this course. So basically, a relation is simply any set of ordered pairs, so we're talking about graphs, that are related in some way. So pretty much any graph that we've got an equation to is a relation, because there is a relationship. Y equals x squared, y equals x cubed, y equals 1 on x. X squared plus y squared is the radius squared. There exists some relationship between the x and the y value. So there we go, there's a circle, x squared plus y squared, 25. Now, a function is a specific type of relation, and such that there's a maximum of one y value for any x value. Now, it's okay for there to be no y value, but maximum of 1. As soon as you get 2 y values for a particular x value, they're no good. It's no longer a function. So a parabola is a function because you could pick any x value and there's only one possible answer for y. Visually, the easiest way of checking it is what we call a straight line test. So you might get a ruler or just your hand or whatever it is. If you draw a vertical line, so one that's parallel to the y-axis, at any point it'll only cut the curve once, if at all. So that's a quick way visually of checking whether or not something is a function. So look at those 4 on the wall there. You've got the parabola, the cubic, the hyperbola, and the circle. They all satisfy the vertical line test, but the hyperbola does, because yes, once you get to the y-axis, there's no cutting of the curve, but that's okay. But the circle, unfortunately, does not. It's fine until you hit the circumference. The circumference, then it's only going to touch it once, but as soon as you go inside the circle, that vertical line's now cutting it twice. So that's how we visually can tell whether something is a function. So here it is, there's the hyperbola, doesn't matter where I put it. Oh look, only cuts it once. So yes, that is a function, as opposed to a parabola on its side, x equals y squared. I can draw a vertical line in, but it cuts it twice at that particular point, so no good. That would just be a relation, not a function. Okay. Now, what we usually find with these sorts of relations, we could actually split them up into 2 functions, the top half and the bottom half. If I was just to look at the top half of the parabola, that by itself would be a function and would have equation y equals the positive square root of x. And the bottom half by itself is a function, and that would be y equals negative the square root of x. But when we put them together, it's no longer a function, it's now the relation. So domain and range are 2 interesting things of functions and relations that we like to look at. So domain, all the possible values of x that you can substitute in and get an answer. That's the domain. So if you think of the function or the relation like some sort of machine, computing machine, and the domain would be the input. They're all the values you're throwing into the machine. So everything that you can go in and it'll get an answer. Now if you're looking for a domain, it's usually easier to look for the values that it can't be rather than the values that it can be. Here's the parabola on the side. If you've got a picture, that's the easiest way of telling a domain, of course, because all you've got to do is imagine you're walking along the x-axis and you look above yourself, you look below yourself and you say, is there a curve there? And if there is, then it's part of the domain. If there's not, it's not part of the domain. So if I was walking along, I'd get a domain, x is greater than or equal to 0. At any point greater than or equal to 0, I could look up and yep, there's part of a curve, there's part of a curve, so it must be in the domain. One of these split functions that we sometimes see, remember coloured in means included, not coloured in means it's not included, it's just the boundary point. And for this one, if I'm walking along, everything's fine. As soon as I go past the y-axis, whoa, where'd it go? It's disappeared. No longer part of the domain. And then we hit 2, and it's not quite there yet, but as soon as we go past 2, the lines come back and we're all very relieved. So the domain for this one is x is less than or equal to 0, and x is greater than 2. What to look for? If you just got the equation and you don't know what the curve looks like, things to look for, some basic ideas. Fractions. We know the bottom of the fraction can never equal 0. So if it involves a fraction, have a look at the bottom of the fraction. because that might give you some points of exclusion from the domain. Basic hyperbola, which we do recognise, I would hope, but just imagine we didn't. Oh, there's a fraction. Bottom of the fraction can't equal 0. So I know x equals 0 is not in the domain. So the way we write that is all real x except x equals 0. You do not write the domain as x can't equal 0. Right? Because a domain is an expression of all the points that are included, not an expression of the points that are excluded. So we say it's all real x, and then we say, oh, except for these points. They're not in the domain. Again, fraction. Oh, bottom of the fraction can't equal 0, so x squared minus 1 can't equal 0. In this case, I get 2 points. X can't equal plus or minus 1. So I would say, oh, well, it's all real x. I can put everything in except x can't equal plus or minus 1. Grammar here is interesting too, because some people say, should we write x can't equal 0 or should we write x equals 0? It comes down to your grammar if you think about it. Because you could say, oh, well, it's all real x except the point x equals 0. So then I'm just saying x equals 0. Or you could say, oh, it's all real 0 except x can't equal 0. So you actually could write either. It just depends on the grammar of how you're saying it. So I wouldn't get too caught up there about the equals to. I tend to write, as you can see, equals to rather than the not equals to. I've got a combination of two fractions there. Well, both fractions must still obey that rule. So I know x minus 1 can't equal 0. That gives me one exclusion. And 7 minus x can't equal 0 gives me another exclusion. So all real x except x equals 1 or 7. Okay, root signs, so radical signs. What do we know about square roots or any even root? You can't find the square root of a negative number. So that might cause some problems. So if I have y equals the square root of 4 minus x squared, which hopefully you recognise as semicircle. Yeah, and it's the top half because it's the positive square root. But all right, imagine we didn't know that. Then I'd say, oh, square root sign. Well, I know that 4 minus x squared has to be greater than or equal to 0. And I can just solve that inequality, x squared less than or equal to 4. And it actually gives me, because I've solved an inequality, it actually gives me the inclusion straight away. So the domain is x is in between minus 2 and 2. Two square root signs, but again, both of them must obey that rule. So I know x must be greater than or equal to minus 3. I also know x must be less than or equal to 5, but both must be true. So I'm looking for the points that are both greater than or equal to minus 3 and less than or equal to 5. So that would be the domain of x is in between minus 3 and 5. Combine the two ideas. Okay, I've got the bottom of the fraction telling me I've got the square root of x plus 2. Well, the square root, x plus 2 must be greater than or equal to 0, but it's on the bottom of the fraction, so it can't equal 0. So this one would simply just be x plus 2 is greater than 0, because it can't equal 0. And that gives me the domain of x is greater than negative 2. Okay, range. The answers, basically. So all the possible y values that you can get by substituting in the domain. So if we think of it like our machine, it's the output, all the answers that are spat out. So here's x equals y squared. Again, if you got the picture, very easy. This time we've just got to get a bit of a rope, climbing rope, and pull ourselves up the y-axis to have a look at this one. But it doesn't matter where we are on the y-axis. As long as I look to my right, there's the curve. So this one, the range is all real y. Really? Oh, yes. Real y. Really? Okay, back to this one. We go climbing up, and we have got a gap in our range, just like we did in the domain. So y is less than or equal to 1. Y is greater than 3 for that one. So if you know the picture, that's the quickest way of finding domain and range. You just look at the picture and go, oh, there's my answer. All right, range, things we look for in the range. Maximum, minimum values. How high up can it go? How far down can it go? So we know that even powers and absolute values, things like that, are always going to be positive, or could be 0, greater than or equal to 0. So if we've got that in our function or our relation, that's going to have an effect. So our basic parabola, actually, we'll pretend we don't know it's a parabola. Y equals x squared. Well, the range will be y is greater than or equal to 0 because I know the square has to be greater than or equal to 0. So that's simply the range. I could never get a negative number there because that square could never be negative. So therefore, if I had x squared plus 3, well, the x squared can never be negative. So I know it's got to be greater than or equal to 0 plus 3. The smallest x squared could ever be is 0. So the range, therefore, becomes y is greater than or equal to 3. Because the square part, smallest it could ever be, is 0. 5 minus x squared. Now, the smallest x squared could ever be is 0, but it's minus. So the least I'm taking away is 0. So therefore, this time it's a maximum. Y will always be less than or equal to 5 minus 0. So less than or equal to 5. It would never go bigger than 5. Absolute value of x plus 2. So again, the absolute value will always be greater than or equal to 0. So in this case, y is greater than or equal to 0. Because that absolute value itself can't go smaller than 0. And similar idea to our parabolas there. If I was to subtract 5 from that, well, the smallest the absolute value could ever be is 0. So therefore, the range must always be bigger than 0 minus 5, negative 5. So looking for those maximum and those minimum values. What's the smallest something could be? What's the biggest something could be? But what if there was a restriction on the domain? When you looked for domain, you found that, no, it wasn't all real x. There was some sort of restriction. Then, not a bad idea. Check the endpoints of the domain. Check the middle of the domain, because you'd be amazed how many of these things are symmetric. And generally, not always, but most of the time, that'll cover the complete range. So there's our semicircle. Pretend we don't know. What is this shape? We found a domain in between -2 and 2. So I'm looking for the range. If I sub in 2, I get 0. I'll also get 0 when I sub in -2 because I'm squaring it as well. So I won't bother subbing in -2. But the middle of the domain is 0 and I get 2. So there's a fair chance that that range is going to be in between 0 and 2. And of course, if you're unsure, just test a few more points and see if you can get it bigger than 2. Fractions. Okay. This time it concerns the top of the fraction. If you've got a constant on the top of the fraction, then that fraction can never equal 0. Because you can't divide a number by something and get the answer 0. Impossible. Yeah. Back to our basic hyperbola, which we're pretending we don't know what it is. So I've got 1 on x. I know that fraction can never equal 0. So y can never equal 0. So my range, all real y, except y equals 0. 5 plus 1 on x. Well, the fraction has got a constant on top, so it can never equal 0. So it can never be 5 plus 0, range, all real y, except y is equal to 5. Haven't got a constant on top this time, so it's not immediately obvious. But if I rewrite this fraction, instead of saying it as x plus 7 on x plus 4, and do a polynomial division, albeit a very simple one, I end up with 1 plus 3 on x plus 4. Now I can see it a bit better. Domain, I can see x can't equal -4. Range, I've got a fraction with a constant on top, so that fraction can never equal 0. So, there's my polynomial division. Look, a remainder of 3. So we can write it as 1 plus 3 on x plus 4. So it can never be 1 plus 0. So there's my range, all real y except y equals 1. So let's talk a little bit about function notation, which is simply this idea of writing it as function x rather than saying y equals. It's no big deal. It's just simply saying, hey, substitute in for x. So function 5, substitute in x equals 5. So it'll be 5 squared plus 4, 79. Now, it doesn't have to be a number. We can substitute in another letter. Function A, replace x with a. 3a squared plus 4. Thank them very much if they give you a question like that. We will see this one a lot later. Function x plus h minus function x. So function x plus h, everywhere I see an x, I'm replacing it with x plus h. So I've got 3 lots of x plus h squared plus 4 minus the actual function itself. So minus all of 3x squared plus 4. Expanding the whole thing out, we got some things that cancel there. Yes, 4 minus 4, 3x squared minus 3x squared, I get 6xh plus 3h squared. Okay, 2f. By the way, something I didn't mention there, but it relates to our graphing, is this is the reason why we put x on the horizontal axis and y on the vertical axis. Remember? Because x is the domain. It's what we call the independent variable. You know, you might have heard of this in science when they're doing graphs, independent variables. And y is the answer. It's the dependent variable, because it depends which value of x you put in to get a value of y. And whenever you're drawing graphs, independent variables go on the horizontal axis and dependent variables go on the vertical axis. I assume they've told you that in science, have they? So it's the same idea, and that's why we have x on the horizontal and y on the vertical.